Okay, AP Physics C. I'm going to be a little bit washed out in this video because it's focusing on the whiteboard, but that's okay. I just want to go over one more of these off of here for you, and then I want to walk you through problem 5, so then you can finish up here. So I'm going to look at part B here. We did this in class, but we did part A in class. Let's take a little closer look at part B, just one more time so you can see the notation here. All right, so we're to find the acceleration at 3 seconds and the displacement from 0 to 3 seconds. So I always do the acceleration first. Make sure I'm not blocking here. Acceleration equals the derivative of velocity with respect to time. So you get quick at this as you do it. So it's 2 times 15, which is 30. Then you take 1 off of the t, so that's t to the 1. Plus 10, all right? So that's the acceleration function for all time. So the acceleration at 3 seconds, you have to plug in 3 for 30, right? So it's 90 plus 10 equals 100 meters per second squared. All right, now, actually yesterday's class we did go through this one here in school. So maybe I should do a different one, but I'll roll ahead with this. You're going to copy this format. All right, so then the displacement, delta x, I'm giving myself space here because we know this is going to take a little more room. Delta x displacement equals the integral from 0 to 3 seconds. Hope you can see this well enough. I have that bigger marker. I should probably switch to that. Delta x equals the integral from 0 to 3 seconds of 15t squared plus 10t minus 60 with respect to time. All right? Yeah, that's quite a bit better. All right. So, the displacement is equal to the integral. Well, the integral is equal to the antiderivative of the function, so 15 times t cubed, so you raise the power, divided by the new power, plus 10t squared over 2 minus 60t, evaluated from 0 to 3. So it's the antiderivative evaluated from 0 to 3. All right, so how do we evaluate it from 0 to 3? Well, delta x, this is 5 times 3 cubed plus 5 times 3 squared minus 60 times 3. All right, so 3 squared is 9. 5 times 9 is 45. Or 27, I guess. 3 squared is 27. Times 5 is 135. Plus 5 times 9, 45. Minus 180. And it turns out to be 0 meters, the displacement. So that's something, and we should be able to examine this function, right? This would represent the initial velocity, negative 60. So it's shot in the negative direction. However, its initial acceleration is actually positive 10. So it's being accelerated to the right. And the acceleration then increases at a rate of 30 meters per second squared each second. So it's going to slow down really quickly and turn around and head back. And it takes 3 seconds for it to slow down, turn around, and get back to where it started. So displacement is 0 meters. Kind of a fun question. All right, let's jump ahead here to number 5. It's a word problem, our first word problem. So I want to make sure you guys are all on the same page on this number 5. All right. Position it so we can see all the parts. Particle starts from rest and has an acceleration of 2t plus 1. assume the units are going to give you meters per second squared here. Determine the initial acceleration of the object. So the initial acceleration, a naught, is the initial acceleration. What does that mean? That means that's the acceleration when time equals 0. So what we do is we just take our acceleration function and put in 0 for time. We get an initial acceleration of positive 1 meter per second squared. Determine the rate of change of acceleration. Rate of change of acceleration is dA dt. It's the derivative of the acceleration. The rate of change of the acceleration. So let's take the derivative of that function. It would be, derivative of that. T, this disappears, it's simply positive 2. What would the units on that be? Well, it's meters per second squared per second. It's how much the acceleration is changing by each second. Sometimes that is called jerk, jolt, or jilt. We typically just write it as dA dt. Determine the speed of the object after moving for 3 seconds. All right, so that's the trick. We haven't done this yet. The change in velocity is the area under an acceleration versus time graph. All right, so I could draw this graph of acceleration versus time. +1, I guess it's got a positive slope, right? Now, I could find numbers here and, do the geometry, but let's use calculus. All right, 3 seconds. So from 0 to 3 of 2t plus 1 with respect to time. I'm going to go up here and do this. Do this on the side here. Give myself a little more room. All right, so you can see it better in the video. All right, so delta V would equal the antiderivative of 2t plus 1. So that would be 2t squared over 2 plus 1 times t, evaluated from 0 to 3. All right? So it's t squared plus t. That's our antiderivative. So delta V ends up being, well, the 2's cancel. So I put them in 3, so it's 3 squared plus 3. Delta V is 9 plus 3 plus 12. Oh boy, is that the end of that? Oh boy, that's the end of lunch. Plus 12 meters per second. All right, plus 12 meters per second. From there, how far the object moves in 3 seconds, that's delta x now. Delta x equals the integral. We have to take that antiderivative now, which is your velocity function, so to speak, t squared plus t, and take the integral one more time, all right? And see if you can't finish that up to find the displacement over 3 seconds, all right? So I'm gonna stop there. Short little video, pause it, go back, email me with questions.